So we've now seen two different solution concepts for normal form games, Pareto optimality and Nash equilibrium. So Pareto optimality is based on kind of group optimality, and Nash equilibrium is based on individual optimality. But because it's game theory and not, because we don't have a single objective function, we needed some kind of extra assumptions in order to talk about what individual optimality means. And for Nash equilibrium, what we do is we say that the players individually optimize given the assumption that everybody else is playing a strategy from the same Nash equilibrium. And that's in some cases a reasonable thing to do, but there are other options. So in this video, we're talking about min-max and max-min strategies, which are about best case and worst case reasoning by players. So instead of assuming that the other players play a kind of fixed strategy from the same strategy profile, we're going to assume that they do something like the worst possible thing, and then we're going to optimize our situation given that everybody else is trying to harm us as much as possible. If we have a normal form game, then we say that a max-min strategy for player I is going to be a solution of this optimization problem. It's going to be a strategy xi that maximizes given that every xj for every other player is trying to minimize, and then we take player i's payoff. So what this means is that this is a sort of defensive choice for player I. So they assume the worst case scenario that no matter what they do, everybody else will do whatever they can to minimize their payoff, and then they're going to maximize that minimum. So this is a literal worst case scenario for player I. We can also equally well define mixed max-min strategies. So we just take maxima minima over sets of mixed strategies, and we take expected utility. Now, this video has quite a lot of kind of slightly annoying, confusing terminology. So these are max-min strategies, and we have min-max strategies. And a min-max strategy, now we say for player I against player J is going to be player I's component of a strategy profile that is ganging up on player J. So we say everybody apart from J is trying to minimize J's utility, but then J is trying to maximize it. If we have a two-player game, this is a bit more straightforward because then you don't have to worry about kind of taking the ith part of the tuple, taking the ith part of this, the solution of this optimization problem. For a two-player game, we can more straightforwardly just write this. Okay, we can also take the kind of the max and min rather than argmax and argmin versions of these. So, so the max min value for player I is the payoff of playing a max min strategy, which is max xi min x everything else, and correspondingly the min max value for player J is the payoff from everybody else playing a min-max strategy against them. Okay, so actually calculating these tends to involve a bit of kind of linear optimization. So let's actually calculate these. Let's calculate these max, min, and min-max turn out to be most often interesting for mixed strategies. So we'll calculate these for mixed strategies. So let's take matching pennies. So remember matching pennies, we have two players who can play heads or tails as their pure strategies. And if they choose the same thing, then player one gets utility 1. And if they play different things, then player 2 gets utility 1. So we have to start by working out the formula for the expected utility for player 1. So if we say that X is the probability that player 1 plays heads and Y is the probability that player 2 plays heads. So X and Y now kind of completely describe a mixed strategy profile, because player 1 is going to play tails with probability 1 minus X, and player 2 is going to play tails with probability 1 minus Y. So the expected utility for player 1 is going to be the probability that both players play heads plus the probability that both players play tails. And because these are independent events, the players are randomizing independently, we can say that it's this, it's xy plus x times y plus 1 minus x times 1 minus y. So now we have to kind of optimize this thing. So say we want to get the max min value for player 1. So how do we do this? Well, for any given x, we need to say, what is the y that will minimize this thing? So it turns out, if you think about it a little bit, if x is less than or equal to half, then the y that is going to minimize this is 1, as is to say, if x is less than or equal to half means that x is more likely to play tails than heads. And player 2 wants to respond to that by playing heads with probability 1. And if we plug that back in, we ended up with, for any given x, this subterm turns out to be this thing. So if x is less than or equal to half, we get x, and if x is greater than or equal to half, we get 1 minus x. So in this case, if x is greater than or equal to half, the y that optimizes this was 0, and then we plug that in. So the graph of this thing is that it's like a wedge. It linearly goes up to 1/2, 1/2, and then it linearly goes down again. So the x that optimizes this is in fact 1/2, and it leads to an expected payoff of 1/2. And we can do the same thing to work out the min-max value for player 1. So when player 2 is playing against player 1. And by the same kind of reasoning, we end up with minimizing this kind of thing. So kind of the same reasoning, but backwards. And we end up with also the value 1/2. Okay, and it's not a coincidence that these values came out the same. So in general, it is always the case that the max-min value is less than or equal to the min-max value. This is a general fact about the max and min operators that's always true. But there's a result called the Minimax theorem, which is one of the oldest results in game theory. So this was proved by von Neumann, which says that if we have a 2-player zero-sum game, then the max-min value and the min-max value coincide. So matching pennies is indeed an example of a 2-player zero-sum game. And it turns out that under the same conditions, this value also turns out to be the payoff from any Nash equilibrium. Okay, so under these conditions, if we have a 2-player zero-sum game, there's also this condition finite that's written on the slides. That's kind of important, but I'm kind of ambiguously sometimes assuming finiteness in games and sometimes not. You usually don't need to worry about this because we're only going to see finite games for quite a while. So under these conditions, we can define the value of a game, which is conventionally this value or these 3 equal values for player 1. So for example, for matching pennies, the value of matching pennies is 1/2.